That's not fair. You're setting us up to fail.
Okay. Actually, that's the first thing I got caught on tape. Okay. Now, it has come to my attention that on Tuesday there is a Siam student chapter event. So that evening, it's actually a fundraiser at Nukes. So if anyone eats at Nukes, or even if you know about the Siam chapter or not, during the hours of I think it's 4 to 8 p.m., then I think what? No, we're just going to be at Nukes, not have class. So yeah, or I'm going to be there anyway. And then the chapter gets a share of the profits. And last time it did this, they got like $300. So yeah, so we can like do stuff.
So bonus points if we come in.
Seven table for seven. We can reserve.
Okay. Yep.
Seriously though, we could sit together and finish this homework. Okay.
Okay then. Yep.
And the kids are good, so I'm probably this.
What?
What is this?
Tuesday.
Yeah. Yeah. Oh wow.
Missing out on free breadsticks.
Yeah, I haven't had it since late 2016. So.
And that I had that in Mountain Group.
Okay.
Yeah.
Okay. So I have about 3.5 pages of notes. So as soon as I get through them, we're done. Well,
How many pages?
3.5. So.
It depends how much you talk in between.
So I should talk less. Okay.
All right.
Okay.
Way to go, Claude.
Way
Way to go.
Well, if we take this to its extreme.
Timing this year.
Yeah. Okay. Or you guys can ask fewer questions.
Ask questions.
Okay, so what I'm going to do is continuing with stationary iterative methods. So I'm going to start by proving that if your relaxation parameter omega is between 0 and 2, let's see, if matrix A is symmetric, positive, definite, and if in addition to that, matrix Q is defined by, we also have splitting, n minus n. Okay. Oh, wait a minute. Sorry, I was trying to state. I ended up stating the assumptions for two proofs at once, so I need to trim this back a bit. Okay. All right. So my ultimate goal is to prove that for omega between 0 and 2, asymmetric, positive, definite, then SOR, successive over relaxation, converges when applied to A. Because I mentioned last time that Gauss-Seidel is guaranteed to converge when when the matrix is symmetric, positive, definite. Well, if we set omega equal to 1, that is Gauss-Seidel. So I'll be proving that. But that'll just fall out of this as a consequence. Okay. But what I'm really going to do first is prove a broader result than this, and that's what I accidentally started to write down at first. So first I'm going to prove the following, that if A is, again, symmetric positive definites, and it has a splitting, m minus n. So this is any splitting for a stationary iterative method, like last time. And the matrix Q is defined to be this M plus its transpose minus A is also symmetric positive definites. So we have all these things true. Then the iteration defined by the splitting converges, which itself is true if and only if the spectral radius of m inverse n is less than 1. So that's really what I'm going to show, but that means that this we get a convergent stationary iterative method. Okay, so once I show this, then it'll be easy to do this. All right. Now, we're actually going to need to work with complex numbers a little bit, strangely. All right, so first I'm going to define B to be m inverse n, which I might add, since n is the same as m minus a, so if I simplify that, that would be the same as identity minus m inverse a. Okay. Now, I'm going to assume that we have an eigenvalue-eigenvector pair of B, because I need to show that the absolute value of this eigenvalue is less than 1. All right. So if I fill in this alternative form of B, then I have that. And then what I'm going to do is I'm going to multiply both sides by m. So that's going to give me let's see, actually, no, not yet. I can distribute, so u minus m inverse a u lambda u. And then I'm going to rearrange a little bit. So I'm going to move this over here, move this over here, and okay, so I have u minus lambda u is equal to m inverse a u. Now on the left side, I can factor out a u to, so I get 1 minus lambda u, m inverse a u. And then I can multiply, now I will multiply both sides by m. And I'm going to swap sides here. So I get au is equal to 1 minus lambda m u. Now, I can't make any assumptions about whether lambda is real or complex. So I'm going to assume that it could be complex. So I'm going to take the inner product of both sides with u. Now, since I think we can go ahead and assume that A is a real matrix, and our splitting is because it's a real matrix. So B itself is real, but even a real matrix can have complex eigenvalues and eigenvectors. So when I take the inner product of both sides, I didn't do this in the notes, but I'll do it here. I'm going to assume that U could be complex. So I'm taking the inner product of both sides with U. I get U Hermitian transpose AU instead of regular transpose like I have in the notes. And we have 1 minus lambda U Hermitian transpose M U.
And that was inner product of both sides?
Yeah. Yeah, so multiplying by vector transpose or Hermitian transpose. It's complex. Okay. Then what I'm going to do is I'm going to take now what we have on both sides is a number. So if I take I could take like the Hermitian transpose of both sides, but that amounts to taking the complex conjugate. So that's going to give me Hermitian transpose of everything, which is transpose and complex conjugate. But A is assumed to be symmetric positive definite. So I don't need any transposing going on here. M is not, well, okay, for M, we're assuming M is at least real. So I could write transpose here, so I'll stick with that. Okay. But now we have this complex conjugation here. Okay. So now I'll just add both of these. So I get 2 UHAU is equal to, all right, so I have, okay. Oh, okay. Actually, no, I don't want to do that. Not yet. Okay. I need to divide by these. So I have now I'll add these two equations together. So I'm going to get U Hermitian transpose M plus M transpose U. And then adding these together, I'm going to get 1 over 1 minus lambda plus 1 over 1 minus lambda conjugate, UHAU. But here we have a complex number plus its own conjugate. So fun facts about complex numbers. If you add a complex number and its own conjugate, you get twice the real part. Okay. So that's what we have here. 2 real part of 1 over 1 minus lambda. Okay. Now, for my definition, I have Q is equal to M plus M transpose minus A. So M plus M transpose is the same as Q plus A. And the thing is, I'm assuming that A is symmetric positive definite. I want to show that Q is also. So I have UH Q plus A U. And then I can divide by UHAU. Okay. And that I can express as
Sorry.
okay. And this I can simplify. Well, this is 1 plus UHQU over UHAU. Okay. Oh, I goofed. What I said earlier. I'm assuming Q is symmetric positive definite in this case. To show that lambda is going to be less than 1 absolute value. Later, when I get to SOR, I want to show that the Q we get in that case is going to be symmetric positive definite. Okay. And this is equal to the expression I have over there, 2 real parts of over 1 minus lambda. Okay. Now, so we're assuming here that Q and A are both symmetric positive definite. What that means is both the numerator and denominator's fraction are positive, because that's what it means to be symmetric positive definite, that this expression is positive, because U is an eigenvector. Eigenvectors are always non-zero. So that's positive. So now what that tells us is finally we can get down to a statement involving only lambda. So twice the real part of 1 over 1 minus lambda has to be greater than 1. Okay. Now, so I'm going to write lambda is alpha plus I beta, the real imaginary parts. So I need a nice way of expressing the real part of 1 over 1 minus lambda. Now, so when I have a complex number like this, I can substitute this in for lambda, but that's not going to really help me get the real part. If you want to get the real part of a complex number that's expressed as a fraction, the best way to do that is, all right, so I'll just take this off to the side here. I'm going to multiply and divide this by its own conjugate. And the reason I'm doing that is when you have more fun facts about complex numbers, z times its own conjugate is the magnitude or absolute value of z squared. In other words, it's real. So by making the denominator real, I can separate the numerator into real imaginary parts and extract the real part that I want. So this is going to be absolute value of 1 minus lambda squared. And now I can fill in real imaginary parts. So I have 1 minus, so lambda conjugate is alpha minus I beta. And then the magnitude, or absolute value squared, is just the real part squared plus the imaginary part squared. Okay. So that means that so twice the real part of 1 over 1 minus lambda is going to be twice the real part of this. So I have 2 times 1 minus alpha over all this. And we know that this is greater than 1. Okay. So let's see what I can do with this. If I rearrange this, I have 2, 1 minus alpha is greater than 1 minus alpha squared plus beta squared. So now I'll expand to the right side, and I get 1 minus 2 alpha plus alpha squared plus beta squared. But the thing is, this lambda is alpha plus I beta. That means that the absolute value of lambda squared is alpha squared plus beta squared. So that's convenient. So now what I have is absolute value of lambda squared is less than, 2 minus 2 alpha minus 1 plus 2 alpha, cancel, cancel, less than 1. So we're done. So all the eigenvalues of B, which is m inverse n, is less than 1, therefore the iterative method converges. So that was pretty fun algebra there. Any questions about any of those wild and wacky steps? Okay. So now let's specialize this. So what I proved here was that if A is symmetric positive definite, and we have a splitting where in Q the dependent splitting is also symmetric positive definite, then we get convergence. So now for SOR, we have the iteration matrix. So M is defined to be, okay. Actually, I hope I didn't do this wrong in the notes last time, although I don't seem to have those. Oh, okay. Right. Actually, can I see anybody's notes from last time? Oh, yeah, this is what I want. Yes. I goofed. Okay, no problem. Easily fixed. Now, first I'll write down what I wrote last time, and then I'll fix it. What I said last time was I had n is equal to d plus omega L, and n is equal to 1 minus omega, d minus omega u. Here's where I goofed. Because when I wrote down SOR, I had these matrices, and I also had plus omega b. But to properly define m and n, it has to be iteration has to be written in a way that you don't have omega b, you just have plain b. So in order to identify m and n, you're supposed to divide both sides by omega. So I actually have to divide both of these by omega. And then you have a proper m and n. Okay. So that's a correction to last time. I keep forgetting about that dang 1 over omega. Okay. Well, I'll simplify this then. So that is 1 over omega d plus L, and then over here we have 1 over omega minus 1 d minus u. Okay, so now we can go ahead and write down so m inverse n is plus L inverse over omega minus 1 d minus u. Now the thing is, the m inverse n that I wrote down last time, I actually called it like t omega, that's still correct. It's equivalent to this because you get an extra factor of omega here and 1 over omega, everything cancels out. But if you're working with m or n individually, you got to make sure it's scaled properly. Okay. So, if we take a look at Q, in this case, that's m plus m transpose minus A. And keep in mind, A is D plus L plus U. Okay. So, we have 1 over omega D plus L, that's M. And then it's transpose 1 over omega D plus L transpose, but A is symmetric, positive definite, so L transpose is actually U. Minus A, which is D plus L plus U. So now we go ahead and simplify that, and we have cancellation all over the place because the L's and U's are all going to cancel. And then all the terms involving D are going to combine. So this condenses to 2 over omega minus 1 times D. Now D is just a diagonal matrix consisting of all the diagonal entries of A. Now, when a matrix A is symmetric, positive, definite, its diagonal entries are yes, they're all positive. So now we just have to make sure for Q to be, so Q is a diagonal matrix. So for Q to be symmetric, positive, definite also, we just have to make sure that this is positive. So, so we need 2 over omega. So we need that to be true. So that just means that omega has to be less than 2. But we've already established that for SOR to converge, we need to have omega between 0 and 2. So everything checks out. So we have Q is symmetric, positive, definite. Therefore, SOR converges for any choice, reasonable choice of the relaxation parameter. Omega between 0 and 2 was established to be necessary last time anyway. So then by setting omega equal to 1, you get that Gauss-Seidel converges for any symmetric positive definite matrix.
So if we want to talk about the speed of converging, it depends on what? The choice of omega will, because since, because it really depends on the spectral radius of this matrix. So depending on how you choose omega, it could turn out drastically differently. Okay. Well, in fact, I'm going to have an example a little later where using Jacobi, Gauss-Seidel, and SOR, so using omega equals 1 versus something greater than 1 really makes a difference. So any questions about all this algebra? Okay. All right. So you say a little bit about trying to determine when an iteration should stop. And there's certain straightforward tests you can use, like if the difference between iterates is small, like smaller than some threshold, you can stop. But how small should that threshold be? Okay. So if so if I let T be M inverse N, so your iteration matrix, and for a convergent iterative method, the spectral radius is less than 1. But we're going to assume something a little stronger than that. We're going to assume that the norm of T, so some norm, is less than 1. Now that's not necessarily true. Any natural norm is always greater than or equal to the spectral radius. So you could have spectral radius less than 1 and various natural norms still be greater than or equal to 1. But we'll assume it's less than 1 in this case. So if I look at the error after k iterations, that's xk minus x. Now each error is equal to the matrix T times the previous error. That was shown last time. So we have T x k minus 1 minus x. But using properties of norms, that is less than or equal to norm of T times the previous error. Okay. And I can pull a little add subtract trick in here. So I'm going to add and subtract xk. Because of course I don't know x is the exact solution. So I'd like to be able to determine stopping criteria in terms of the difference between two successive iterates, xk and xk minus 1. So using triangle inequality, this is less than or equal to T times the difference between consecutive iterates plus norm of T times the norm of the error after k iterations. But now what I can do is I can move this to the other side. So now I have 1 minus the norm of T as k minus x less or equal to T times the difference between my consecutive iterates. So now I simplify this. So the error after k iterations, I may not be able to compute that, but it's bounded by norm of T over 1 minus norm of T times the difference between
Dr. Lambert, when you did the triangle inequality step, should the very first x2 xk be xk minus 1? Or should one of them be xk minus 1?
Yeah. Okay. Something like that. Okay. So now I have this bound on the error, because at least this is something I can compute. Now, the norm of T, of course we want to stick with a norm that's easy to compute, like the 1 norm or the infinity norm. The trouble is it's M inverse N. So that may not be so practical to compute either, but in certain cases, like, well, certainly for Jacobi, it's easy to compute, because M is just a diagonal matrix. So for Jacobi method, you could definitely compute this norm of T. But what's interesting is what it says that convergence can be slow if the norm of t is, now it has to be less than 1 for convergence, or we're assuming it is, but if it's really, really close to 1, then what happens here? That this denominator could be small, so the whole fraction could be large. So you get a situation where the difference between your consecutive iterates is nice and small, but this error could still be relatively large. So that's something to be aware of. Well, besides, the spectral radius of t, that not only tells you whether your method will converge, it also indicates the speed at which your iteration will converge. So spectral radius is only slightly less than 1. You can expect a slow convergence anyway. But if it's possible for you to estimate this, at least, then it's a good idea to set your error tolerance with this in mind. That, like, let's suppose you want, like, if this turns out to be, like, 100, because this is so close to 1, then, and you want an error tolerance of, like, 10 to the minus 8, then you should look for this to be less than 10 to the minus 10. It's just like there are situations where you can easily compute a residual. And you might think, oh, residual is small, therefore the error must be small. Maybe not. In fact, that's happened in someone's research, or one of my students, where we're able to get residual to be nice and small, but the matrix is so ill-conditioned that the error is actually enormous. Unfortunate. Okay. So any questions about this? This is stopping criteria. For stationary iterative methods.
So can we say that if error is small, then residual error is also small?
Actually, that's not necessarily true either. But if error is small, we're happy. That's definitely true. That's one way to think about it. Okay. Okay, I still have. Well, I've only gone through 1.5 of these 2 pages of notes.
We'll be here.
Okay. Now, actually, this section is something I only added to the notes the last time I taught this class, because there's a particular homework problem coming up in the next homework, in 3, that is particularly painful. It's a MATLAB exercise. So this section is meant to help.
What number in homework 3? Exactly.
I don't remember. So you actually start looking at homework 3? Or? It's one about solving a differential equation.
They might get good fast.
I got it right here. It's the one about what?
About solving a differential equation. Well, it's actually
Part B?
yeah, it is a part
Part C of what?
of problem 2, I think.
Part C and problem 2.
There's like 5 pages and there's only 3 problems. You can't say there's 1 problem and then do like A through Z. That doesn't really count.
Okay, fine.
I mean, you just as soon said, hey, you have 8 problems in homework.
Okay.
Let's see. Okay, this is.
Okay. So the typical differential equation to solve is Poisson's equation on a rectangle, or use a square. Poisson's equation is the Laplacian view, which is second partial with respect to x plus second partial with respect to y is equal to some function of xy. So now, if the f is 0, you know this is Laplace's equation. But when you have something on the right side, it's Poisson's. We'll assume x is between 0 and 1. That's x and y both. And we have homogeneous Dirichlet boundary conditions. So any of you 606 veterans, this will be familiar to you. All right, so we assume that, like for instance, when x is 0 or x is 1, then we have 0. And also when y is 0, y is 1, we have 0. Okay. All right. So for illustrative purposes, I'm going to let f be a function that satisfies these boundary conditions, like sine pi x times sine 2 pi y. That'll work.
That's an equal sign, not a double prime, right?
What?
That's equals.
Yeah.
Equality.
That's y equals.
Yes. Yeah, it's a tilted equals. Okay. All right. All right. So, the first thing to talk about the second derivatives in one dimension. So now this is what's commonly referred to as a BVP, boundary value problem, as opposed to, for instance, an initial value problem that's time dependent. Okay. So to handle differentiation, I want to get a system AX equals B that approximates this equation. So for that, I use the center difference approximation. So we have f double prime at grid point xi is fx minus 1 minus 2 fxi plus fxi minus 1 I plus, oh wow, okay, it's supposed to be xi plus 1. In the notes, it actually says x minus I plus 1 because that is supposed to be an underscore, not the minus. So, whoops. Delta x squared. We're assuming equal spacing. Okay, so we have xi is I times delta x. I goes from 1 to n. And delta x is 1 over n plus 1 because we only care about the interior points for solution because we know the solution is equal to 0 in the boundary. So this covers all the points in the interior. So we have n plus 1 interior points that can lead to n plus 1 subintervals around them. Okay. And we have boundary conditions similar to the 2D problem. So f of 0 and f of 1 are 0. So that means that if I define a vector f to be value of x at these interior points, and then the vector g is meant to be an approximation of f double prime at these same interior points. Okay. Then I can say that G is A times F. So I'll get an approximation using this matrix A, where the entries of A come from the coefficients of this differentiation rule. So I have minus 2's all the way down the diagonal, 1's above for these points, and then 1's down below for these points, and then I have to divide by delta x squared. So this is a n by n matrix. Okay. Okay, there's something, wow. Yeah, something's wrong in the notes. I have an extra column for some reason. The entries, yeah. I can assure you that's the correct matrix. Because because I've written them down like 5,000 times in my career. I don't know what happened in the notes, so I guess I have a few things to fix. Okay, 1 page left. Okay. So, but this is useful for second derivative in 1 dimension, but we have a 2-dimensional problem. So I need a matrix that will compute second derivatives in the x or y direction on the whole rectangle. Okay. So for that purpose, I can define a Kronecker product. Alright, so A, Kronecker product B. And we'll assume A is n by n, and B is p by q. So the sizes do not have to relate to each other at all. So the whole product is mp by nq matrix that can be most easily defined this way, where you basically tile B but each tile is multiplied by the corresponding entry of A. So I have A11B, A12B, and so forth. A21, A22, up to A2M, then AN1, or M1, and then AMN. Okay. So then what I'm going to do is I'm going to order all of the points on the grid. So I want to represent a function in 2 dimensions, also by a vector. Now that's straightforward in 1 dimension, like I wrote over there, but what about 2 dimensions? So I can order them as follows, like x1, y1, x2, y1, and xn, y1. So I go for the x's, but all the y's stay the same. And then I go to the next y value, x1, y2, x2, y2, so forth, down to x2, xn, y2. And then I keep going until I get to xn, yn. All right. So when I do that, notice that as I go from one point to the next, the x value is what's changing between consecutive points, whereas y only changes n points apart. So for partial derivative with respect to x, to represent that, I can use my matrix A over there for a second derivative, and I can use identity Kronecker product A. And what that does is it just puts A all along the diagonal. So it's performing second derivative for all the different y values, but with respect to x. And if I go the other way, with the Kronecker product, that's going to tile identity according to the pattern in A. So I'm going to have -2 identity all the way down the diagonal blocks. And we're going to have identities above and identities below. So to differentiate with respect to y, remember neighboring y values are n points apart, so it has to go into the next block to get them. Okay. So now, for my Laplacian operator, that'll just be the sum of these two. Well, I'll call that result matrix L. So identity quantum product A plus A quantum product I. So that is the matrix I need for my system of equations. And I can use this ordering to describe my right-hand side. Where I take my function f of xy from my Poisson's equation and just evaluate it at all of these points. So I'm going to solve LU is equal to F, where L is my matrix that I get from here, where A is my one-dimensional second derivative matrix. And then F is defined as follows. So if I evaluate F at x sub I, y, j, based on how I've ordered the points over there, this is the index where we need to go. So the index of my y value narrows me down to a block of n points, and then I indicates where within that block of n points my x value goes. So in this case, that would be sine of pi I delta x sine 2 pi j delta y for all ij from 1n. Okay, so things like this we'll be doing in that one part of that homework problem. Okay.
One part of that, one homework problem.
Yes. Okay. Now, because of properties of the Laplacian operator, L is actually symmetric negative definite, all negative eigenvalues. So this means that minus L is symmetric positive definite. So, in closing, what I can do is apply the various stationary iterative methods to this problem, to solving LU equals F. And so what happens is, all right, so if I try 100 iterations, and I can compute the exact solution, like analytically, of this particular PDE, so I can use that to measure error. So if I do 100 iterations of each of these methods, Jacobi, Gauss-Seidel, and SOR with omega equal to 1.785, then here's my error after 100 iterations. So it's really, the way error is measured is the 100th iterates minus the 99th iterate, 2 norm, relative to the 2 norm of x100. So this gives me a rough error estimate. So what I get is, well, not very good. For Jacobi, it's 3.5 times 10 to the minus 3. For Gauss-Seidel, a little better, 1.1 times 10 to the minus 3. And then for SOR is 5.7 times 10 to the minus 10. So finding the right value for that relaxation parameter omega can really pay off. Now it's interesting to note the spectral radius of M inverse N in these three cases. So for Jacobi, it's 0.9927, so that's pretty horrible. It's so close to 1. So it's not surprising that the error would they'll be pretty large. And then for that's strange. I don't even have it here for Gauss-Seidel. Not sure why I didn't include that. Okay. But SOR, it's much less. So 0.7849. So, and it doesn't have to be that much smaller to have convergence that much faster because that spectral radius is being raised to a power. So if it gets, well, to give you an idea, by iPhone calculator, if I take 0.9927 and raise it to the 100th power, I get 0.4806. So you don't get much error reduction. Whereas if I take 0.7849 and raise it to the 100th power, I get too many zeros to count. Okay, so so about 3 times 10 to the minus 11. So that gives you an idea as to what kind of spectral radius you really like to have. Okay, well, I got through all the notes. So I didn't have to take the whole class time. So no class Tuesday, because I will be at Nukes, and maybe some of you will be too. And on Thursday, we will cover the very famous conjugate gradient iterative method. Yeah.
In case of 3D, how I can write those
Oh,
Kronecker products?
you do a threefold Kronecker product where with identity twice. So
Oh, identity twice.
yeah, so one order gives you with respect to x, one with respect to y, and one with respect to z.